A rectangular concrete beam with a cross-section of 250 mm by 500 mm is reinforced with 425 mm diameter tension bars and 216 mm diameter compression bars, allowing 60 mm center of bars from face of beam. Determine the following maximum steel ratio for single reinforced action using strain of 0.004. So we only have two conditions of strain to achieve a maximum steel ratio. So first is at a strain value of 0.005, but in this problem, it is indicated that we will use this other condition. So this is the other condition, strain equals 0.004 in determining the maximum steel ratio. Okay, so let us solve first for the effective depth. So that is 500 minus 60, so that is 440. So using the equation of the strain, so we will substitute the value of 0.004 here. So we can solve for the depth of neutral axis required. T equals 188.5714286. And then we can now compute the depth of compression block. So that is 0.85 of 188. So now we can compute the area of steel. So again, we go back to C equals P. Then 0.85 FC prime AB equals ASFY. Then we substitute 0.85 FC prime 250 times A equals ASFY. So we can now compute the maximum steel area. That is 1723. And then to compute the maximum steel ratio, we just divide AS by B times D. B is 250 and effective depth is 440. Therefore, the maximum steel ratio is 0.01566, and that is letter B. The next question is depth of compression block. We are asked to solve for the actual depth of compression block. So therefore, we will now consider the given reinforcements. Okay. By the way, let us discuss first the rectangular concrete beam in the problem. Okay, so in this problem, as you can see, we are reinforced with 425 diameter tension bars and 216 millimeter diameter compression bars. So meaning, we have reinforcement in the tension side and we also have reinforcement in the compression side. Basically, there's a chance that this is a doubly reinforced section. So for doubly reinforced section, we are considering an additional compression reinforcement in determining the strength of the beam. And then, as you can see, when determining the moment capacity, we just add the couple created by the compression reinforcement to the initial couple created by the force in the concrete and the tension steel. Previously, when we are dealing with singular reinforced, no, yung mga na-solve natin previously, ito lang siya, no? Kumbaga, yung force na nakikreate ni concrete at yung tensile force na nakikreate ng steel, so kung ano yung couple na nakreate nun, yun ang ating moment capacity. And then, kapag meron kang compression reinforcement, we just add up the couple being created by the compression reinforcement and the corresponding reinforcement in the tension steel. Okay? The process is still the same. We will start with equilibrium because it is important, of course, that the compressive force created by the combined concrete and compression steel is equal to the force provided by the tension steel. So that is 0.85 FC prime AV. Ito pa rin yung kaninang expression natin, force in concrete. And then, nadagdagan lang siya ng AS prime FY kasi nga, ino-consider na natin yung bakal sa itaas. And then, we equate that to ASFY. This is the area of tension reinforcement times Fy. We have an assumption that the stress in the steel equals Fy. Okay, so this is the standard assumption that the steel yields. Okay, so we substitute the values 0.85 FC prime 250 plus area of the compression reinforcement times 415 and then area of tension steel times the yield stress So we can solve for the value of A. Next, we are computing for C because we need to check if we have a valid assumption that Fs is equal to Fy. So let us compute for C. So 145 divided by the beta, which is 0.85. The value of C is 170.8272711 millimeters. Okay? So we can now compute F prime S. So that is equal to 600 times C minus D prime over C. So that is 600 times 170.8272711 minus 60 over 170. Okay, so by the way, for the stress in the compression steel, so this is the formula. Okay, 600 times C minus D prime over C. So we substitute. So the value of the stress in the compression steel is 389 megapascals. Next, we check the stress in the tension steel. So that is 600 times D minus C over C. So kapag tension steel naman, ito naman ang formula, no? D minus C over C. So that is 945.42 megapascal. So as you can see, the tension steel yields, but the compression steel does not yield because the computed value is still less than 415. Therefore, we have to repeat the process because it is not valid to assume that Fx prime is equal to Fy. But for the case of tension steel, the 415 in the right side of the equation is already correct. Okay, so tama na itong nasa right side kasi nasa 945 yung computed value natin, mas mataas sa 415. Pero ito, hindi pa tama. So we have to revise again the equation. Konting revision lang naman yung gagawin natin so that we can arrive with the true value of A. So we repeat. Instead na Fy, we have replaced it by Fs prime. Okay, so we insert the values 0.85 Fc prime, B is 250, and then A, we replace A by 0.85 C. This is beta times C. And then AS prime is 2 pi over 4 times 16 squared. And then we have to replace Fs prime because it does not yield. So meaning we have to insert here the formula for Fs. That is 600 times C minus 60 over C equals 4 pi over 4 times 25 squared times 415. Okay, so we can now solve for the value of C. We can now compute the new value of A, that is 0.85 of C, and that is 147.26. So this is now the correct value of A, and that is letter A. Okay, next, stress in compression reinforcement. So we are asked for the stress in compression reinforcement. So let us just substitute the computed value of C in the formula 600 times C minus D over C. And that is 392. And that is letter B. Okay, next, ultimate moment capacity. Again, as I have said, so in determining the moment capacity for doubly reinforced section, so we just add the couple created by the compression steel and the corresponding tension steel with the previously concrete and the corresponding tension steel. Okay, so we have AS prime Fs. So I have used here Fs because we have already proved that the steel does not yield. So we have AS prime times Fs times moment arm. The moment arm is D minus D prime. So here I have chosen to take moment about the tensile steel. So that is 0.85 Fc prime AB. Then the moment arm is D minus 0.5 of AB. So let us solve. This is the first part, AS prime times Fs prime times moment arm. Then the second part is the 0.85 Fc prime of the area of concrete times D minus 0.5 of A. So the nominal moment strength is equal to, so for the first part, that is 599,310.75. Then for the second part, that is 240,756. So the nominal moment strength is 300,687,219.3 Newton millimeter. Okay? But this is just the nominal moment strength. So we have to compute first the strain of the tension reinforcement for us to determine the reduction factor to be used. Because recall, the reduction factor depends on the value of the strain. So let us compute for the value of the strain, 0.003 D minus C over C. So that is 0.0046192988843. And then here's the value of the reduction factor. Okay? Because as you can see, our strain is greater than the yield strain but less than 0.005. Again, our section falls under the transition stage. Therefore, this is the formula of the reduction factor to be used. We have 0.65 plus 0.25 strain minus Fy over Es over 0.005 minus Fy over Es. So the value of the reduction factor is 0.867. So therefore, we can now compute the ultimate moment capacity. We will just multiply this by the value of Mn, that is 260.83 kilonewton meter. And that is letter B.